traditional pacemakers, or we call them transvenous pacemakers, have a generator / battery with the rest of the circuitry under the usually left collarbone, and up 1 to 3 leads pass through the venous system, the veins, coming from the arm, and into the venous system and pass into the heart, where they kind of gently screw into where they're supposed to remain. These have been around a long time, tried and true, beautifully engineered devices. The challenge is that when you have these leads in your bloodstream for years to decades, there are a few long-term complications. One is long-term infection risk, both at the time of implant or long-term accumulating, as every year goes on. The leads are bending with every beat of the heart, so they can have a risk of mechanical failure that also accumulates over time. And then lastly, they can compromise the actual venous system. So the veins through which they pass can actually sort of clamp down around them, which is not as scary as it sounds as it would be if a coronary artery was blocked. But in patients who need other hardware or dialysis fistulas or catheters that use their veins, it can be a limitation. So leadless pacemakers came along. The first human implant was 2014 to try to overcome a lot of these limitations of transvenous devices. They virtually eliminated the infection risk. The leadless pacemakers are pretty small, about a half to a third the size of a AAA battery. And the whole thing is encapsulated. The pacing electrode and the battery are all in one, and they reside entirely within the right lower chamber of the heart, the right ventricle. And by virtue of being that way, virtually zero infection risk. Obviously, they don't block the venous system because they don't reside within it. And there certainly can be mechanical or electrical failures, but they're not flexing with every beat of the heart necessarily. So there isn't necessarily a mechanical fatigue factor to them. So they've really been a game changer in a lot of ways. I always start with the fact that our technology is very early, and it's a proof of principle. And there are attempts at doing energy harvesting in other parts of the body, and including other attempts using the heart. But ours is unique in that we are trying really hard not to change the size, form factor, implantation method of the leadless pacemaker itself. We simply aim to replace the outer housing with a piezoelectric material that is able to convert mechanical energy into electrical energy. So this idea came about because a lot of my research time and my laboratory and collaborators' expertise is in ultrasound, both diagnostic and more so therapeutic ultrasound. And ultrasound transducers take a voltage, we put in a voltage, and they put out a pressure, because sound and ultrasound are ultimately just pressure oscillations, right? And the materials we use for ultrasound transducers are part of a broader class of materials called piezoelectrics. So as an electrophysiologist who often sends patients for these leadless pacemakers, I came up with this idea along with some of my colleagues of the fact that these devices are residing inside the right ventricle, which has its own natural pressure oscillation. So can we find a piezoelectric material that can harness this effect in reverse and capture this oscillation of pressure as the right ventricle squeezes and relaxes, and then convert mechanical energy into electrical energy, the opposite way that we traditionally use piezoelectrics for ultrasound. Yeah, I was very fortunate. I only came to University of Washington about a year ago, and one of the several reasons I joined the institution is that it's one of the few medical schools where the hospital and the medical school is on the same campus as the undergraduate and graduate campuses, particularly the engineering school. And I have an engineering background, but that goes way back to my bachelor's degree days. And since my research does operate in medical devices, it's very convenient to have a wide array of engineers with whom I can work. And so shortly after I got here and came up with this idea, I initially set out to find students and collaborators. So fortunately, at University of Washington, we have great engineering departments. So a group of master's students from the bioengineering department in the Master's in Applied Bioengineering program joined this project with me. And we got them, set them out on a path and a direction to try to remain within the engineering constraints of not changing the size and form factor of the device. And in a remarkably short amount of time, Abby, Jedi, and Kevin, 3 very talented master's students, were able to get a prototype up and running. And then we tested it initially on a benchtop using just flat flat pressure simulator, which we presented at AHA. And then we shifted to a benchtop cardiac pressure simulator, into which we could dial physiologic systolic and diastolic pressures at a simulated heart rate of 1 beat per minute, and test our prototype to ensure that it could indeed harness this energy and convert it from mechanical to electrical. We then, frankly, did a lot of calculations to figure out exactly how much energy were we harvesting, how much would it potentially prolong battery life. And using fairly safe assumptions, we estimate that we're able to harness about 10 to 11% of the energy needed to pace the next beat. And so we have a long way to go, but I'm really proud of my students for coming this far in a remarkably short period of time, really less than one academic year. Since then, we've identified more collaborators and more students who are joining this effort. One of my dear friends and collaborators, Dr. Mohammad Malakouti in the University of Washington Department of Mechanical Engineering. And I think with his expertise and others, we're really going to take our Gen 2 device to improve to higher levels of energy harvesting efficiency. I think the next step is to improve upon the 10 to 11% energy harvesting. That's probably not a game changer in my mind. We have a lot of great ideas in how we plan to do that, some of which are proprietary, but it will obviously involve new fabrication methods of the housing and other ways in which we can increase the piezoelectric effects. We're going to do that and revalidate it in the way we did for the prototype and the benchtop model, but we subsequently plan to do a chronic long-term implantation study to confirm that this effect we see in a benchtop cardiac pressure simulator has a similar efficacy in a beating heart and is safe to implant for a matter of weeks to months. So that's an obviously important next step. What we will also look forward to at AHA, as we get feedback on this initial proof of principle presentation, is what does the audience think is a game changer? We obviously are very biased. This is one of our homegrown projects. What percentage of energy harvesting do we need before a provider, an electrophysiologist, is willing to entertain a new version of a device they're already used to implanting? Do we have to prolong battery life by 10%, 20%? We're interested in what patients are going to care about. And finally, the medical device companies, we're not going to invent a brand new pacemaker. In reality, if this works and if it does progress as we anticipate it will, the best path for this is to partner with a strategic partner, one of the large pacemaker companies, to incorporate this feature into the next generation of one of the leadless pacemakers. So we're interested in their feedback as well.